Quantum theory, it is the physics that describes the microscopic world. So it's the physics that describes atoms and the makeup of atoms, electrons and protons and neutrons, and elementary particles like photons and crazy particles like neutrinos. So all of the microscopic world, the constituents of matter and energy, are described by quantum theory.
Can you tell me what entanglement is?
Right. Entanglement's a really important and kind of crazy aspect of quantum theory. It was so crazy that Einstein called it spooky action at a distance. And you know, Einstein was probably the most famous physicist of all times that we know. And what entanglement is about correlation. The fact that you can have two things that are highly correlated and you bring them separately into two different places and still they know about their correlation. No matter how you look at them, they have this correlation. And it seems to be really spooky. It's as if something over here is affecting something over there, even if they might be on different sides of the galaxy. Now, I should be clear, it's not like you can communicate faster than the speed of light with entanglement. It's not that something is affecting something that you can send a message, and Einstein knew that. Nonetheless, it's really such a strong and different correlation, so different from anything we understand in our everyday macroscopic experience.
So you see our soccer players, they're moving at the same time as each other. What do you think about that?
Yeah, they're really demonstrating some of the aspects of entanglement. The fact that if one kicks and the other sees an opposite kick, and no matter what direction they are, there is a relationship between them. Their movements are choreographed, they're correlated. Now, I should be a little bit careful. There are correlations that we have, just like you just saw with our soccer players. We call those classical correlations. The real entanglement you can only do at the microscopic scale. But we'd like to try to make it happen in the real. Maybe someday in the future we could entangle soccer players.
Can you tell me about the idea of superposition?
Yeah, superposition is an incredibly fundamental concept in quantum theory. It's the idea that there can be, say, two things that might happen, but we can't say which. But it's more than probability. It's the idea that these two things kind of exist at the same time. So like when I flip a coin, the coin is going around. It might be heads, it might be tails. It's one or the other. We just don't know which one it is. But in the microscopic world, it's kind of both. It kind of can exist in this limbo land of one or the other. And until someone observes it, until we look at it and make a measurement, does the system collapse into one choice or the other? And that's really a critical concept in quantum theory. It's kind of like, you know, the Zen philosophy. If a tree falls in the forest and it does, you know, no one's there to hear it, does it make a sound? And that's really a kind of, there's this sort of philosophical aspect of superposition. Does the system have this property or not, or not until we actually observe it? And so I think that this idea that we see the soccer player, if the fans aren't there to cheer, did the goal really happen? Kind of the idea, yeah.
What is cloning?
Okay, cloning. So that's another part of, yeah, this is jargon in quantum theory. There's something called the no cloning theorem, right? And make it fancy by calling it a theorem. And what it says is, you know, if I have some information. Suppose an eavesdropper wants to check out a secret message. So she can look, somehow she taps into the phone and gets the information. She might want to copy it. And to copy it is to make a perfect copy, is to call it a clone. Just like there was a famous sheep that was the first sheep that was cloned. It was called Dolly. and that was a clone of the embryo. It was a perfect copy, like a twin is a clone. But when you make a copy, we call that cloning the information. It turns out that's impossible to do in quantum theory. That's the no cloning theorem. There's no way, without knowing what it's going to be, without knowing what you're trying to copy, to make a clone. And that no cloning theorem is actually very powerful because it tells us that we can protect information from eavesdroppers with quantum mechanics. So that's an example of quantum information. That is an example of the technology that we can build with quantum theory.
Okay. Can you explain to us what probability is?
Right. Probability is a really important concept. Probability is about chance. Probability is about assigning a chance to something when we don't know what's going to happen. Like when we flip a coin, it flips and we don't know for sure whether it's going to land heads or tails. And so we assign a probability. And if we don't know if it's a fair coin, we might say it's a 50% chance of heads or a 50% chance of tails. That's the probability of heads or tails. And we use probability in our everyday life all the time. We look at apps on our phone to see what the chance of rain might be. Of course, in Albuquerque, that's typically close to 0, but every once in a while, it might be 30%. And so why do we assign a probability? Because it's impossible to exactly predict whether it's going to rain or not, given the models we have. But what's special in quantum theory is that even if we had the best information we possibly could have, we still don't know what's going to happen. Quantum theory says things are intrinsically random, and there is therefore only we can say is what's the probability when we do a measurement whether one outcome will happen or another.
Okay, and then, so here you see one of our United Soccer players demonstrating probability. What do you think about that?
Well, these are excellent players, and so if I were to assign a chance or a probability that they're going to score, I would assign a pretty high probability, probably over 90%. You know, every once in a while they might miss. So I don't know for sure whether they're going to hit the goal or not, but I think there's a pretty good chance. So I would assign a pretty high probability to them scoring a goal, maybe over 90%.
Ooh.